Salam alaikum. Our lesson today is about regular languages and finite state automata. Presented by me, Buatsa Halima, Assistant Professor at University of Warkla. Introduction. A finite state automata is a fundamental tool for computation and modeling in discrete mathematics, used in many fields, formal languages and compilation, communication protocols, process control, etc. It is the abstraction of any system that can be in a finite number of states at different times. However, in this course, we consider that an FSA is an abstract machine that allows you to read a word and assert its membership, or not, in a language L. The first part of this chapter is devoted to FSAs, their representations, and their variants. In the second part, we study regular expressions and their properties. But what is a finite state automata? A finite state automata is the simplest abstract machine, program, that recognizes regular languages, type 3, it does not use any memory. In which a FSA is formally defined by a quintuplet, x, q, I, f, sigma, where x is a finite set of symbols, the letters of the alphabet. Q is a finite set of states. I is the initial state, I belongs to Q. F is the set of final states, F is a subset of Q. Sigma is the transition function, defined from Q times X to Q. Let's pass to the representations of the FSA. There are three main representations for FSAs. The first one is the matrix representation. The second one is a form of a labeled directed graph, while the third one is in the form of a function. We illustrate these different representations through the following example. Let it be the FSA defined by the quintuplet x, q, I, f, sigma, such that x equals a, b, q equals q0, q1, initial state is q0, while the finale ones equals q0, and we define the following transitions. Sigma, q0, a, equals q0. Sigma, q0, b, equals q1. Sigma, q1, b, equals q1. The first representation is the matrix representation. The previous example will give us the following matrix where the first column represents the set of states and the first row represents the set of letters of the alphabet. We notice the appearance of the symbol of flesh to say Q0 is the initial state and the symbol of the double circle to say that Q1 is a final state. Here is the graphical representation. As shown in the following figure, we represent an FSA by a labeled directed graph. The nodes represent the states, the edges represent the transitions in which the letters of the alphabet are the labels of the edges. The initial state is represented by an incoming arrow while the final states are represented by a double circle. The third FSA representation is the representation as a relation. This is a binary relation between two sets. The first contains all possible combinations of pairs, state, letter of the alphabet. The second contains the states of the automata. The arrows connecting elements of the first set to elements of the second represent the transitions. Note that the initial state and the final states must be defined as sets. This is illustrated by the figure. Initial state equals Q0 and F equals Q1. As we mentioned in the introduction, the raison of using FSA is recognizing type 3 languages, so let's take a deep look about language recognized by a FSA. Let a sad face X, Q, I, F, delta, be an FSA. Firstly, definition of a configuration. The configuration of the FSA, at a certain time, is given by the current state of the FSA and the word that remains to be read, current state, word that remains to be read. The initial configuration is Q0, W, where Q0 is the initial state of the FSA and W the word submitted to A, to be recognized. The final configuration is given by QF, epsilon, where QF is a final state and the empty word indicates that there is nothing left to read, the word belongs to the language. Let's pass to the definition of a direct derivation. A configuration, Q1, is said to directly derive the configuration, Q2, W, if and only if delta, Q1, A, equals Q2 where delta is the transition function, A belongs X and W belongs X star. We denote by Q1, directly derived from Q1, W. And finally, the definition of an indirect derivation. A configuration, Q(W1), is said to indirectly derive another configuration, P(W2), if and only if there exists 0, 1 or more direct derivations that, from Q(W1), lead to the configuration, P(W2). We denote by P(W1), indirectly derived from Q(W2). Definition of the language recognized by a FSA. The language recognized by the FSA, denoted L(A), is defined by L(A) equals W is an element of X asterisk operator slash Q0, W equals asterisk operator QF epsilon, with QF is an element of F. Note, a FSA recognizes one and only one language, but the same language can be recognized by several FSAs. A word is accepted by an FSA if, after reading the entire word, the automata is in a final state, QF is an element of F. A word is rejected by an FSA in two cases. The automata is in state G, the current input being A and the transition delta, Ga, does not exist. We say that the automata is blocked. The automata manages to read the entire word, but the output state is not a final state. Let's pass to the equivalence of FSAs. We say that two FSA A1 and A2 are equivalent if and only if they recognize the same language, L, A1 equals L, A2. Examples: the shown figures present that the following FSAs recognize the following languages. Thanks for your attention. Next session, inshallah, we will see the second part of this lesson, which is devoted to the regular languages.